Hi guys, welcome to today's session where we are going to be looking at gradient descent. But a quick overview, let me review what we did in the last class. So in the last class, we looked at cost function, right? We looked at linear regression with one variable. Then we looked at the central dogma of machine learning, right? From training set to learning algorithm. Then we look at the hypothesis, right? How we map the feature to the output variable, which is h. We looked at y equals to mx plus c, which is the formula for simple linear regression. Then we changed our constants, right, to theta 0 and theta 1, right? And then we changed our y as well to h of x, right? Then we looked at cost function, and we were able to look at gradient descent, but we looked at cost function in details, right? So we looked at our x feature, our x variable, our feature, and then our prediction. We looked at how we can make our prediction very close to our output variable. We looked at different characteristics of our 2D graph based on different values of theta 0 and theta 1. Remember when theta 0 is 0, the graph starts from from the scratch. Look at theta 1 here, right? And then the value of theta 1 of theta 0, and then value of theta 1 gave it this property, right? So you can look through it on your own later. And then we talked about cost function, that the idea of cost function is to choose the value of theta 0 and theta 1 such that our h of x, our prediction, is very close to our y for our training examples. And we said we measure the accuracy of our hypothesis, this hypothesis, right, which is h. We measure the accuracy of our hypothesis by using a cost function. Now, what's the formula of cost function? Right, this is formula of cost function. Right, we have j theta 0 and theta 1, which is this is our cost function. The formula is 1 over 2m. M is the number of training examples into a summation of h of x, which is our predicted price, our prediction, minus the actual value, all squared, right? We also said that this is also called the squared error cost function, or the squared error function. We said that loss function is used to refer to the squared error function for a single training set, and cost function is for the entire set. So we said theta 0 and theta 1 are parameters, or constants, and this, of course, is the formula for our cost function. Then we looked at the 2D example, right? We looked at how our cost function minimizes theta 0 and theta 1. But we first said that let's make theta 0 equal to 0, just so that we have just one parameter to look for, and it makes our case very easy, right? So if theta 0 is 0, then our h of x, which used to be theta 0 plus theta 1x, would now be theta 1x, right? And this is what our cost function is going to be. Instead of theta 0, theta 1, we just have theta 1, and then we have our cost function, and then our graph will give us something like this. So we said if theta 1 equal to 1, we are going to have a perfect fit where our h of x is equals to y, and then our cost function is going to be at the global minimum, right? So this is what we want in machine learning, where our h of x, right? So we solve for j theta, which is our cost function, because 1 over 2m this, right? And this gave us 0, right? So you can take your time to look at it. This is our perfect, perfect cost function where j theta equals to 0. That means that our predicted value equals to our given value, right? We looked at another scenario where theta 1 equals to 0.5, and we saw that our predicted value was very far from our actual value. We calculated our j theta, right? And it gave us 0.85, which is what we have here, right? And we looked at one more example. If theta 1 equals to 0, you can see how far our predicted value is from our actual value. Then we calculated our j theta, which is our cost function, and we have 2.33. So we have our j theta here. Now, if we compute all this on a straight line, right, for the first one, second, and the third one, what we'll find is that we have a convex function like this, right, where j theta moves from here down here. what we want, like I've told you, is we want our j theta to be at the global minimum. This is called the global minimum, right? So we want our j theta to be here. Then I explained what do you call it? I explained this is unnecessary for now. I explained span and linear combination. So today we are going to go into gradient descent, but I would like to show you how gradient descent looks. Where is that? This is our j theta versus our theta. In the former class, I showed you j theta versus theta in 2D because we had only theta 1, right? So it looked like this. But in 3D, where we have theta 0 and theta 1, this is how our cost function looks like, right? Of course, you know that we are good. We want to get to a global minimum, but this time around, we have two minimums. We have 1 year and we have 1 year, right? So this is called a local minimum. Let me write it down. It's called the local minimum. When we have two, the biggest one, or when we have just one, is called a global minimum. So for example, let's say we initialize our theta 1 and theta 2. What we do in machine learning is that we just initialize theta 1 and theta 2 at a random point. Right? So let's say we initialize them here, which is what we have here, right? Cost function time after time. Remember from here, let's say we initialized our theta 1 year, then it moved here, then it moved to global minimum. That's what we do in machine learning. So cost function moves from year to year, right? It moves from year to year. It moves from year to year. Then it moves from year to year. Then it moves from year to year. Then from year to year and from year to year. Then we arrive at a local minimum. Let's say we start our initialization around here, right? This is how cost function is going to move from year to year, 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 from year to year. This is basic machine learning, right? The machine is learning from your data. This is why it's called machine learning, because machine wants to get to the point where your theta 0 and theta 1 have the lowest possible value. And at this point where the theta 0 and theta 1 have the lowest possible value is the point where your machine learning model is most accurate, right? So I need you to really understand that. But this is the math. That's just an intuition. This is the maths, right? Remember we did cost function. That's why I took my time to take you through cost function once again. Remember that cost function, so we have some function which is j theta 0 and theta 1. We want the minimum point, right? So what we usually do in machine learning is that we start with some random values of theta 0 and theta 1. Then we keep changing it to reduce the cost function. And hopefully we end at a minimum, which is what I showed you here, right? So you keep changing it, keep changing it, keep changing it, then you end here. If we started here, for example, right? So it keeps going, keeps going, it keeps going, keeps going, it keeps going, it keeps going, it keeps going. You want to end at this local minimum, right? So I did a screenshot because I didn't want to be writing this out. It's very hard to write on my laptop, right? So let's look at that screenshot. Do I have? Good. So this is the gradient descent algorithm, right? I need you to write this down. I'm going to explain everything bit by bit. So this is the gradient descent algorithm. Let me see if I can write it down, right? So at theta j, if it doesn't work, if I'm not able to write it, we'll just use the screenshot to explain. So at theta j, which is our gradient descent, equals to, look at this assignment stuff, is very important. This is not equal to, this is an assignment. I'm going to show you, I'm going to explain that. So we have theta j minus alpha d over d theta j into our cost function j theta 0, theta 1. Right? This is an assignment. This is not equal to is an assignment. And I'll give you the difference. So we have assignments, our normal assignment, right? Which is something like A, then 2 dots, followed by an equal to B. We are just basically saying that whenever we get the value of B, right, transpose it into the value of A, right? For example, we can have a assignment. It's supposed to be a tick dot, but I don't know how to do tick dots here. Okay. All right, equal to assignment A plus 1, right? So this is an update. Once you get A plus 1, let's say 1 is 2, right? Let's say A is 1, right? So A plus 1 is 2. We update it. The moment the value of A changes to 2, 2 plus 1 is 3. It keeps updating. It's an update. Unlike when we have a truth assertion, right? Where we say A equals to B. This is a truth assertion. So A, for example, can never be equal to A plus 1. Because this is a truth assertion. This is not an assignment. But yeah, we are assigning whatever we get here into here. So I'm just updating the value of A. So that's what this is. So whatever we get here, we're just updating it into theta j, right? What else? This is called learning rate. I'll explain learning rate in details later. It's called learning rate, and it controls how big a step we take on our way to global minimum. So for example here, we had a very decent learning rate, right? So learning rate determines how big a step we take, right? So we can have, so let's say this learning rate is 1. If we decide to have a learning rate of 2, so one step will move from year to year, and that step will move from year to year, and that step will move from year to year. If we had a learning rate of 0.5, one step will move from year to year, the other step will move from year to year. So learning rate just determines how big a step we take on our way to global minimum, right? What else is there to explain? Then this part of it, so this is learning rate, right? Then this part is a derivative term. So I'm going to explain all of this. Don't worry, it's very simple. Right. So the next thing is simultaneous updates. Let me show you a screenshot of what I mean by simultaneous updates, right? So what we do in machine learning is that we have theta, we are solving for theta 0 and theta 1, right? So look at this. We are solving for theta 0 and theta 1. So he updates theta 0 and theta 1 simultaneously. So we get that theta 0, theta 1, he updates, then we get another value of theta 0 and theta 1, he updates, then we get another value of theta 0 and theta 1. So that we're talking about with simultaneous updates here, right? Unlike when we don't have a simultaneous update, right? So we have, we solve for theta 0, we solve for theta 1, you update. Unlike when you solve for theta 0 first, right? Then you first update before you solve for theta 1. The new value of theta 0 is going to be used to solve for this new theta 1, which is going to affect the entire algorithm. So that's why we call it a simultaneous update. Right. If that is understood, then we now go into how gradient descent, how we use gradient descent, right? So let me explain. I'm going to explain this derivative term right now. So let's use a very simple example. Please, if you don't understand this to this point, I want you to go through last class, understand cost function, right? I want you to understand cost function. Let me, for emphasis sake, let me write this down. So gradient descent is used to minimize cost function. It's an algorithm that is used to minimize cost function. It's not only used for linear regression. We use gradient descent for all the other machine learning algorithms that we have, right? So gradient descent is used to minimize cost function. So you want to take your cost function to the global minimum, right? You want to take your cost function to the global minimum. We use gradient descent to move from, let's say, from here to here, or from here to here. So that's what we use gradient descent to do. So let's go. Let's take a very simple example now. This class, I think, will be divided into two. It will be divided into two. So, it's used to minimize cost function, right? So let's minimize the cost function for just one parameter once again, just so that we can understand it, right? So let's minimize cost function. One parameter or one constant, right? That would be like theta one, right? Just for to make it understandable. Remember here in our last class, we decided to make theta 0, 0, right? And use just theta 1, just so that we could understand this. So we're about to do the same thing here, right? So we are looking for the minimum. We're looking for the minimum of j theta 1, right? So we're looking for the minimum of theta 1, where theta 1 is a real number. Where theta 1 is equals to a real number. Very important to state, right? So let's try to understand one gradient descent we do on this function. So remember that I told you that in machine learning, we start at a very random value for theta. So we start at a very random value. So let's say we have our gradient descent. So this is j theta. This is j theta 1. And then this is theta 1. This is theta 1. So this is our gradient descent. All right. So let's say we start somewhere here. All right. If we decide to start somewhere here, gradient descent will update as theta 1. This is an assignment function, don't forget. It's a tick dot, right? Will give us theta 1 minus alpha, then d theta. So if you've not done calculus before, don't worry yourself. You don't need to. You can go and take a calculus refresher course anyways. This is j theta, but it's very simple. I'm going to show you what happens in calculus now. So this is the formula to calculate to get to our global minimum for j theta or for theta 1. So what derivatives do is that they take the tangent to the point. So there's a tangent to this line. There's this point at the tangent. I'm sorry, I didn't draw this convex this curve well. But on a real curve, we are going to have a tangent like this, right? And what happens is that we just calculate the slope of the line. So derivative, taking the derivative, calculates the slope of the line. You can go and take a refresher course on calculus, a very short course. You'll find out that when you take the derivative of the point on the line, all you just do is you take the slope of the line. Right. So this is just supposed to give you an intuition. We're not supposed to go into the deep math because it's going to confuse you. Right. So look at this slope. Right. This slope has a positive number. So this line has a positive slope. I'm writing it down just for emphasis sake. Has a positive slope. I don't have time to prove that to you. So this line has a positive slope. For that reason, we're going to get a positive number for our derivative. So this is our derivative. Because this line has a positive slope, we're going to get a positive number for our derivative. So therefore, theta 1 is will give us theta 1 minus alpha, which is a number, and times a positive number. Times into a positive number. What does this mean? What this means is that theta 1, right, is going to be updated into a negative number. We're going to have a negative number here for theta 1. So what this means if we have a negative number is that since we started at this point, right, since our theta 1 started at this point, right, the slope is going to move in this direction. So we're going to move in this direction until we get to global minimum, right? If you don't understand that, I'll do the second example in the opposite direction, just so that you can understand that. Okay, let me do another example. So let's say we have this once again, right? And then we have our here. So yeah, we started on this side of the line. Here we also start on this side of the line. So this is, let's label this as well. This is j theta 1. Theta 1, and this is theta 1. So our formula again, theta 1 would give us theta 1. So I'm just updating the value of theta 1, right, into our linear, which is the real number, into the theta g of theta 1. Right, so we are looking at what's happening in this derivative thing, right? So we are looking at how this derivative is done. So once we take the derivative of this line, we have under slope, right? We have under slope. Good, this looks better. So we take the tangent to the line, right, to this point, and then we get the slope. Obviously, right, because of time, I won't be able to prove that again, but this line has a negative slope. I mean, slope of a line is as basic as possible. Just take the difference between here and here, right? So this line has a negative slope. So for that reason, I'm going to have theta 1 is assigned to theta 1, the former value of theta 1 minus alpha, which is our learning rate, into a negative number. Right? So it's going to be a negative number. This means that theta 1, our new value of theta 1 is going to be, so this is minus times minus, so let's say this is minus 2, for example. Let's say this is minus 2. Minus times minus will give us plus. So our theta 1 is going to give us a positive number. Right? Going to give us a positive number. So that means that the new value of theta 1, the former value of theta 1 was somewhere here. Right? So it means that the new value of theta 1 is going this direction. So theta 1 will keep going this way, this way, this way, depending on the learning rate, till we get to the global minimum. Right? So that's just an intuition into what happens. So lastly, let's look at learning rates. All right, so let me just explain the intuition behind learning rates. If you miss it at some point, then go back at some point in your notes and then read it to the point where we are, so that you can have some understanding. On Friday, we would have an explanatory class. That's the way it will fit my schedule this week. Okay, so let's look at learning rate now. So this alpha is called learning rate. Let's look at how alpha affects gradient descent. Because when you get to deep learning, right, you are going to be able to, you are going to fix your learning rate yourself. So you need to know what learning rate means. So let's write, if learning rate is too small, gradient descent will be slow. If learning rate is too small, so you're going to give your algorithm a fixed learning rate. You'll be the one to set your own learning rate yourself. The computer won't fix it for you. Right? So if learning rate is too small, the algorithm will be slow. What do I mean? So if we have this as usual, and we have this, right? We have our curve, right? If we start here and your learning rate is too slow, then your learning rate will move from here to here, and then move from here to here, then from here to here, then from here to here, then to here, then to here, then to here. I mean, this is going to be too slow. It's going to take you a month to get to your global, for you to get here, or this is where you want to get to your global minimum. If learning rate is too small, it will take you a long time to get to your global minimum. This is J theta 1, and this is theta 1, right? So that's what happens if learning rate is too small. But let's look at what happens if learning rate is too big. If learning rate is too large, gradient descent can overshoot the minimum. It will fail to converge. Right. So once again, let's look at what that means. So for example, like I said, remember I told you that when we start in machine learning, we just take a random value of theta, the cost function. This is theta 1. So we just take a random value. So let's say we start here at this point. Of course, we want to get to the global minimum, right? But if the value is too large, what you have is it can move from year to year, right? And then it moves from year to year. And then it moves from year to year, right? So you want your cost function to converge at the global minimum, right? But if the learning rate is too large, what you have is that it's going to overshoot your minimum, and you will never be able to arrive at your global minimum. So what you do in machine learning is that you fix you once you see that your theta is not your j theta is not converging, right? If it's not reducing, then you just have to reduce your learning rate if it's too large. Right. But I have a question for you. I have a question that I want you to solve. If you've been following, then try to solve this question yourself. It's a very simple question. Right? It's a very simple question, but try to solve it yourself. Try to have a deep understanding of this shit, right? And solve it yourself. The question is that when theta 1 is already at a local minimum, so let's say we have so when theta 1, we have a graph like this. Because it's not every time you're going to have a simple curve like this. It's not every time you have a simple curve like this. Right? So let's say we have something like this. So we have two local minimums, right? We have one here, and then we have another one here. Right? The question is that when theta 1, this is theta 1, this is j. Theta 1, right? So take some time to answer this question. When theta 1 is at global minimum, sorry, at local minimum, what will one step of gradient descent do? When theta 1 is at local minimum like this. What will one step of gradient descent? I'll give 5 seconds or 10, 20 seconds, right? So just pause and try to answer the question yourself, right? So look, just think through when we have your theta, that, and it wasn't at your global minimum or local minimum, right? One step in gradient descent behaved in some type of way here. One step in gradient descent behaved in some type of way, depending on the value of your learning rate. But now, when we've gotten to our global minimum, or in this case, our local minimum, right? What will one step of gradient descent, what will it do, right? Will it move in this direction, or you move in this direction? That's another clue. Will it move this way, or will it move this way? If you understand the topic very well, then you would be very correct. Right. So our let me answer the question now. So we are at this point in theta one, right? So our current value of theta one, our current value of theta one. What's wrong with my mouse? Of theta one. Going to be an assignment of theta one minus learning rate alpha into the theta of my cost function. This is theta one of our cost function. Right. So at local, to answer your question, at local optima or local minima, whichever one, or local minimum, whichever one, derivative will be equals to 0, because there's nowhere it's going to again. At a day, but after a day, we've already gotten to where we want to get to, right? So once you do machine learning and you find out that your theta is not changing, the theta is not changing, right? Then you've gotten to your local or your global minima, right? So that means you have your most accurate model, right? So therefore, what we have is theta one, right? Will give us theta one minus learning rate alpha times 0, right? So therefore, our theta one will equals to theta one minus 0. So theta one will be equals to theta one, right? So when we get to our local or global minimum, gradient descent will result into nothing. So the answer is nothing. Nothing happens, which is our dream, which is where we want to get to, which is this initial point we did where we got to yesterday, right? This point, right, is our global minimum, our local minimum. This is where we want to get to. This is the point where h of x is equals to y. This is the point where our predicted price equals to the price that we have in real life, right? So that's the end of this class. In the next class, I'm going to be putting gradient descent to cost function in real mathematics. So thank you. Please make sure you understand this class before the next one. Thank you.